Hi everybody, this is Olenjolai Moko from the beautiful and fantastic country, United Republic of Tanzania. I would like to welcome you into the sessions or into period or session 9 of the module of the subject known as Advanced Chemistry. And the main topic we are learning is General Chemistry. First of all, I would like just to welcome you to the YouTube channel called Tanzania Online A-Level Secondary Schools in square bracket OLENJOLAIM. And then departments which is serving you today is Advanced Chemistry, and the subject is Advanced Chemistry. The main topic is General Chemistry, one of the Form 5 topic. And then the topic is the atomic structure, right? And then the class is pre-Form 5 and Form 5 students. Also, this material will be useful for the Form 6 for the Form 6 students, diploma students, and even undergraduate students who are pursuing some modules in chemistry, because you know this is stuff a little bit too much details compared to the basic chemistry. So in case you want to offer your Thanksgiving offering, as you have been informed in an introduction video for this channel, then you may send your seed, we call it seed Thanksgiving, in this telephone number. But in case you want to do the bank transactions, then you go to the descriptions below. You'll get too much details concerning about it, how you can offer your seed Thanksgiving offering. So before we start today's sessions, which is session number 9, I would like just to do a brief review, quick review of lecture or session 8. So this is of period 8. So in period 8, basically we have been doing solving problems or problem solving. We call it solving problems or problem solving. Okay? Basically we have been using the Planck's mathematical formula or mathematical equation, right? And this is, we say that change in energy is equal to Planck's constant times the speed of light over wavelengths, and this also is equal to Planck's constant times frequency. But another equation which is famous that we've been using is Rydberg, right? Rydberg equation. So in Rydberg equation, we have 1 over wavelengths, then have Rydberg constant 1 over n1 square minus 1 over n2 square, right? But later on, we combined the Rydberg equations and the Planck's constant in some cases. That we have Rydberg constant, speed of the light, Planck's constant, 1 over energy level 1 minus 1 over energy level 2, etc. So in case that you want to add details on what I've been reviewing, please, in this channel, go and take a look on what? On a period or session 08. So in today's lecture, we are still proceeding with atomic theories, which is a very important subject in chemistry, right? Especially for advanced chemistry. And today I have prepared too much details on Heisenberg, Heisenberg. This is a mathematician, a German physicist who did a lot of experiments on the atomic structure. Okay, so it means that's our discussion. So Heisenberg uncertainty principle, and this physicist, he was actually trying to examine. So he did a lot of experiments and read the papers published by the Bose, right? So and then he come up with some mathematical formula. That's what I like from them, because whenever they do an experiment, they don't end somewhere else. They end with something called mathematical formula, which make chemistry to be beautiful, and especially atomic structure. So today we are going to learn about Heisenberg uncertainty principle, and that's what I want you to join me. Please stay tuned. Let us go to the business. Heisenberg, so this subtopic is called the Heisenberg. Say with me, Heisenberg. Possibly you may pronounce it improperly comparing to me, but that's not the matter. The matter is to understand the content. Heisenberg uncertainty. So this is called Heisenberg uncertainty. Heisenberg uncertainty principle. Heisenberg uncertainty principle, right? So Heisenberg, so this is R, uncertainty principle. So pronounce Heisenberg's uncertainty principle. So it should be powerful when you pronounce these words. This is the German physicist. Okay? So first of all, before we start, we state the principle. We say that winner Heisenberg, okay, was a German physicist, who did many experiments. Regarding the position and the momentum of electron in the atomic structure. Okay? Atomic structure. So then, after many experiments, he published his principle that is known as Heisenberg uncertainty principle. So his principle based on uncertainty. So the basic question which you might be asked is state the Heisenberg's uncertainty principle. That's the basic question. Okay, how do you state this Heisenberg uncertainty principle? So it states that it is not possible at any moment to predict accurately both position and velocity. Both position and velocity or momentum. Of an electron. In an atom simultaneously. Yes. That's how the principle states. So according to Wiener Heisenberg, the German physicist, he said that it is not possible, it is not what? Possible at any moment to predict accurately, not just to predict it, you can predict it, but to predict it accurately, both position and velocity, or in bracket momentum, of an electron in an atom simultaneously. So it's not possible, according to him, it is not possible. Don't when we ask you to state, don't underline anyway. I'm trying to underline the keywords. It's not possible at any moment to predict accurately both position and velocity or momentum of an electrons in an atom simultaneously. You can predict the position of electrons, and also you can predict the momentums of velocity of electrons, but not simultaneously according to Heisenberg principle, right? So it means you cannot do these two. So it means that the principle based on the fact that it's not possible to deal with those two physical quantities. So before we tell you the reasons, mean that we say that the physical quantities, before just to tell you why the physical quantities, okay, the physical quantities in his experiment are two. The first one, positions of electrons, positions of electron in an atom, okay, in an atom. And then the second physical quantity is momentum, or in other words velocity, because velocity times mass of electrons, we get the momentum of electron. Where do you find that electron? In an atom. Okay? So why it is not possible to determine or to predict accurately both momentum and the velocity of the electrons? That are the questions that we have on the stage. There are many reasons, but I have found two. Okay, why? So the question is, why it is not possible? Why it is not possible? Why it is not possible to predict both velocity and momentum, or velocity and position of electrons in an atom. So he said that according to Heisenberg, we have two reasons. The first reason is this: the size of electrons is very small, such that the radiations of high energy with very small wavelengths are required to predict it at disturbing positions and speed of the electrons. The size, the first reason we say that the size of electron, subatomic particle, which is negative charge, is very small. Very small, right? So this is very small, such that the radiation of high energy level, the radiation of high energy level, the radiations of high energy level the radiations of high energy level, the radiations of high energy, not level, energy, with very small wavelengths, with very small wavelengths. So if I write this one, is that the symbol for wavelengths, you have length, are required. You're learning chemistry. Okay, are required to predicting, to detect, not to predict, sorry, to detect. To detect it. Thus, disturbing, that's disturbing what? Disturbing position and the speed of velocity and speed of electron. That's the first reason. Let me explain details. What does it mean? The questions on the stage is why it is not possible to predict both velocity and rate and positions of an electrons in an atom. According to Heisenberg, the size of electrons, he said that the size of electron, right? The size of electron is very small, such that the radiation of high energy with very small. So because of the size of the electrons is very small, right? Then we need radiations of high energy with very small wavelengths. So this is what is required to detect it. And because we require that radiations of the higher energy with small wavelengths, what happens? So in case we apply to the atom, then that situations will disturb the actual positions and the speed of electrons in an atom. What does it mean? For instance, for example, suppose that this is the nucleus of an atom, and then this is the shell, right? Suppose that you have electrons at this position, right? And then we supply what you supply high energy. So according to Planck, we say that change in energy is equal to Planck's constant times frequency. Or in terms of wavelengths, we say that change in energy is equal to Planck's constant times speed of the light over wavelengths. Right? So with this equation, we find that change in energy is inversely proportional to wavelengths. Right? So according to the first series, we say because the size of electrons is very small, we need high energy. High energy is required. High energy radiations is required to be supplied. So it means that when energy will be high, because the energy is inversely proportional to wavelengths, the wavelengths will be small. So they're inversely proportional. So even if that we supply this high, it means that we supply, let's say, high energy, means that high energy, and then with short wavelengths. That's how we call it in physics and even in chemistry. With short wavelengths, then what is going to happen? So when we supplying to this atom, okay, these are the two properties that we supply to this atom in order to determine the position of these electrons and its velocity of revolving, because we say electrons always is in motion, orbiting what? The nucleus of an atom. So it means that when we supplying this onto the atom, what's going to happen? The positions of these electrons will be disturbed. So rather than finding it here, you can find that now the electrons won't be there where we expected to get it. Possibly find that electrons is here. But so this is not the accurately positions of electrons. But it has been, this position has been disturbed because of what? Amounts of radiations have been supplied to it. Number two. Second reason. So on other hand, if that's the case, that's the challenge. On other hand, if the radiation of low energy with what? With longer wavelengths. So remember that this is the symbol for the wavelengths, lambda, with longer wavelengths, right? Will be used or will be supplied, say that will be supplied, will be used, then the position of electron, will not be detected. So you see that's another challenge. So if you say that, okay, I will use the low energy radiation. Radiations will be using the radiations with low energy, right? And then because remember that as we said, this is inverse proportional. So then we say that now I will use radiations of low energy. And hence, but in case if I reduce the energy, hence I'm going to increase what? The wavelengths, right? And hence the wavelength is longer. The longer wavelengths will be used. Then the positions of electrons will not be detected. So that's another challenge. It won't disturb the positions of electrons, but now we cannot achieve what you've been looking for. Okay, in case you have any question concerning about ongoing lecture, ask your question in the comment section, and other students worldwide will answer your question effectively, or even myself, I can come or I can answer your question. So he said that according to this challenge, if one term, meaning that if one, either positions or speed, if one physical quantity remains at position or momentum or velocity is determined, So then we say that according to this challenge, if one physical quantity, positions of velocity is determined, then we say that then the other is determined accurately. So if we manage to determine the positions accurately, then the other now, the second physical quantity, is less accurately determined. That's the challenge. So now, according to Heisenberg, to find the absolute positions of an electron, so we can have the mathematical formula. So we say that Heisenberg established also, or derived the mathematical formula that is used to determine position of what? Position of electron. position of 40 of electron. And this mathematical formula is, we say that change in positions means a small change in position times small change in momentum. This is equal to Planck's constant over 4 pi, so it is constant. So this is mathematical questions of Heisenberg. So let me define symbols. So the mathematical formula is changing what? So it means that the mathematical Heisenberg mathematical formula is changing x times change in momentum. Then this one is equal to Planck's constant over 4 pi. So that's what I want to discuss with you right now. What does changing in x represent? So changing in x, this one represents a phenomenon that we call uncertainty in measuring position. So this is uncertainty, that's why we call it uncertainty. That's a big uncertainty. So it's uncertainty, uncertainty in measuring position of electron in the atom in meters. The SI unit is meter. And hence delta P is equal to uncertainty in measuring momentum of an electron in atom. And this, the unity is, so in SI unity of meter for this. For this one, the SI unit of the unit is in kilogram. So unit of 40 of kilogram meter per second. So this is the SI unit. So we have also to solve some mathematical problems in this concept in order for us to understand clearly. So again, when we dig further into this Heisenberg uncertainty principle, mathematical equation, we say that change in position times change in momentum, this is equal to Planck's constant over 4 pi. So here I have to define also Planck's constant. So this is Planck's constant that I taught you in previous lecture of this topic. And this is 4, this is pi. So on the right hand side you have the just like expressions, the division expressions, the products and division expressions of what of the constant. Okay? So according to Heisenberg, what do we say that? We do remember that we have to say that, first of all, in experiments, so according to Heisenberg experiments. okay, when he was doing experiments and computations. Experiments. He said that the value of what? The value of products of changing x and changing momentum is slightly larger than, slightly higher than the value of what? The value of Planck's constant over 4 pi. Right? So what does it mean? We say that if we take the small change in x, we multiply with a small change in momentum, then this is equal to what? We say that it's slightly, means it's closely, it's smaller than Planck's constant over 4 pi. Right? So this, in some of the books, we have this kind of mathematical formula. Okay? So this means that it's closer, but it's not equal to the Planck's constant over 4 pi. Again, if we dig it in, Heisenberg again say that, again, from what? From the concept that momentum is equal to mass and velocity. And in this case, in order to get change in momentum, always we do expect that the velocity is the one that we expect it to change. Right? So change in momentum is equal to mass and change in velocity. So it means that if this is the second equation now, and this was the first equation, so if we take the second equation and substitute in the first equation, we have what? Small change in x, then we multiply by mass times small change in velocity. This is equal to Planck's constant over 4 pi. Right? So in case that we need the positions of electrons, we say that a small change in x is equal to what? Is equal to Planck's constant over 4 pi times mass of electrons, then small change in what? In velocity. So this is a very important mathematical formula. Or in case that we need to find the momentum, or whether that we want to find the velocity of electrons, so you see that this the mathematical formula determines the position. So you say that the mathematical formula of Heisenberg mathematical formula of Heisenberg that is used to determine position of electron in what? In the atom is given as this, that small change in x is equal to Planck's constant over 4 pi times change in momentum. Or if we know the velocity of electrons, we say that, or the small change in x is equal to Planck's constant over 4 pi times mass of electrons times small change in velocity. So both of these formulas will be used. Okay? So again, we say the mathematical formula of Heisenberg determine the positions. So we say that for determination of what? Of velocity of electrons. So we say that the Heisenberg will be like this. Small change in velocity is equal to Planck's constant over 4 pi is mass of electrons times small change in what? In position. So this is the mathematical form. So now you are well in Heisenberg mathematical formula for computation. So soon I'll be doing the computation or by using those questions, so that you may enjoy the beauty of what? The beauty of again we say that The Heisenberg equation. Heisenberg equation. Heisenberg equation may be